Okay, hello everybody, and welcome to this extra little video that I'm creating to deal with the overrun of the live session this week. So in the live session, we looked at some k-anonymity examples, and what I really want to get around to as well is just a slow walkthrough of one of these randomized response questions. And in particular, what I was going to look at was question 2 from the first set of checkpoint exercises. So in this question, what we're wanting to do is estimate the proportion of all students who are using study drugs in the current exam season. And we're going to denote this proportion by P. Of course, whether or not you use study drugs is quite a sensitive topic, and so students might not be willing to respond honestly if we ask them that directly. So what we're going to do is introduce a randomized response design to this survey, so that students are given some sort of plausible deniability in their responses. If someone comes back to them and says, oh, hey, you said that you took study drugs in this survey, what's going on there? They have some deniability where they can say, oh, no, it was just the randomness in the system that told me to respond yes. What this leads to is a sort of bias variance trade-off, where if we introduce a large amount of randomization here, what we're doing is hopefully decreasing the bias in our responses, so getting the students to respond more honestly. But that also comes at the cost of increasing the variance of our associated estimate of P. So we're adding more noise to our data, and we're not going to be as able to precisely estimate this population quantity P from our sample of data for the same number of samples. So how exactly are we going to implement this randomized response? Well, we're going to go up to each student and ask them, have you taken performance-enhancing drugs during this exam season? To which they're either going to respond yes or no. The way in which they respond to this question is going to be determined by two draws from a random number generator. The first draw is going to determine whether or not they reply directly or give a randomized response. And the probability of giving a direct response is going to be 1 minus Q, and the probability of giving a randomized response is going to be Q. From a second draw from this random number generator, those people who were in the randomized response category are going to reply yes with probability Q, and they're going to reply no with probability 1 minus Q. Okay, so the people in the randomized group, we know which proportions they're going to reply yes and no in the long term, but we don't know for each individual subject whether they gave a direct response or a randomized response and which of the randomized responses it was that were chosen by them. Okay, so the first thing that this question is asking us to do is draw a probability tree to describe this survey. And this is going to have three phases. The first one is the true status of whether or not the student uses study drugs. The second one is going to be whether the student is assigned to give a random response. And the final one will be whether they agree or disagree with the statement, so whether they respond yes or no. So we've been given some notation in the question about how to denote this. So study drug use is the random variable D, so D if they do use study drugs, and D complement if they don't. Similarly, randomized response is an R if they're assigned to give a random response, and R complement if they're responding directly. And we'll have these for each of these two arms of drug use. And then finally, we've got whether or not these students agree or disagree with the statement. So do they respond with a yes, why, or a no, why complement? And I'll fill the rest of this in as we work our way through. So starting from the beginning then, we know that the population proportion of students who take study drugs is P in our notation. And so the proportion that don't are 1 minus P. We then look separately for each student and say, okay, are they being asked to answer directly or in a randomized way? And they respond directly with probability Q and indirectly or in a randomized manner with probability 1 minus Q. And that's going to be the same regardless of whether or not the student has actually taken study drugs. And what this means is that because these two parts of the probability tree are independent of one another, we actually could have written these the other way around. We could have first considered whether or not the student gave a random response and then considered drug use afterwards. So we could have had these two layers of the probability tree in the other order. And then finally, filling in this final stage, we know that if the student is giving a non-random response, so if we're in this top branch, so the student has taken study drugs, and we're then following this line to give a non-random response, there's only one possible answer that they could have given here. And that is a yes with probability 1. So then considering the other arm coming up here for students who have taken study drugs and are assigned to the randomized response, then they will respond yes with probability Q and no with probability 1 minus Q. And we can fill in the bottom half of this probability tree in a similar way. So we're going to have two options for students who give a randomized response, yes or no, and the students who don't give a randomized response are guaranteed in this case to respond no, which I should really write as Y complement. And then all we have to do here is fill in the corresponding probabilities. So again, this is going to be probability 1, this is going to be probability Q, and this is going to be probability 1 minus Q. And now we have it, a completed probability tree. Okay, so the second part of this question asks us to write down what the probability is that a student replies yes. So one way of doing this is to start out with an expression P of Y, the probability of a yes response, and use the law of total probability to expand this out into all of the different cases we can have with our two random variables, R and D. Another way of doing it that is perhaps a bit simpler to see is just to look at this probability tree and say, in order to get a yes response, we need to be on one of these three arms of the probability tree. And because each arm is independent, that means as we're moving along each, the probability of reaching the end is simply the product of probabilities along that arm. And because arms are independent of one another, the total probability of an outcome of yes is simply the sum of the probability of each of these ways of achieving yes. And that is essentially what the mathematics of applying the law of total probability says to us. So here we've got three different ways of achieving yes. The first one has probability P times 1 minus Q times Q to get along to this top arm. The next one down occurs with probability PQ, where I'm dropping the probability 1 of responding yes, because we know that that student has taken study drugs. And the final way of achieving yes is the upper arm of the lower branch. So that we get with probability 1 minus P, 1 minus Q, Q. 1 minus P, 1 minus Q, Q. Okay, so we have an expression here, but we can simplify it down a little bit. So what I'm going to do is pull the common factor of q out the front here. So that leaves us with a p times 1 minus q plus p plus 1 minus p times 1 minus q. Okay, and we can do a little bit of further simplification by expanding out these brackets. So here we're going to get a p minus pq, excuse me, minus pq plus p, and then in this quadratic expansion we're going to get plus 1 minus p minus q plus pq. So we can get some terms simplifying down here. So what are we going to have cancelling? We're going to have this p cancelling with that p, so we just end up with 1p overall. We have this minus pq cancelling with this plus pq. So we're left with a plus 1 and a minus q. And that is as simple as we can get this expression. Okay, so relatively straightforward, either applying algebraic laws of probability or through inspection of the probability tree. But what this gets us is an expression for the probability of a particular response in terms of the true probability that we want to estimate and the randomization probability which we control. Okay, so let's suppose that a particular respondent called Janine replies yes. The next part of the question is asking us what is the probability that she has not, so that she has not taken performance-enhancing drugs. So what I want to do here is apply Bayes' theorem to get an expression for the probability that the student has not taken drugs given that they've responded with yes. So by Bayes' theorem, that is going to be the probability that they don't take drugs and they respond yes, divided by the probability that they say yes. Equivalently, this is just the definition of a conditional probability in terms of the joint and marginal distributions. So what we can do then is use the probability tree up above to substitute this in. So the probability of not taking drugs and saying yes, if we scroll back up, is the probability of not taking drugs and responding yes. There is only one way to achieve that, and that has probability 1 minus p times 1 minus q times q. So that was 1 minus p times 1 minus q times q. And the probability of y we have just calculated, that was q times p plus 1 minus q. And we can simplify this down a little bit because our q's on the numerator and denominator will cancel. And that's as simple as we can get for this expression. Okay then, moving on to D, this is getting into the estimation portion. So what we're being asked to do is derive the method of moments estimator for the population proportion of students who take drugs. And we've been given a bit of notation to do this. So we're going to let our responses be denoted by yi for each student, I equals 1 to n. And that is going to be a binary indicator variable, taking the value 1 if student I answers yes, and the value 0 if that student answers no. So what we can do is take our previous expression for the probability that yi equals 1, which I'm going to use slight abusive notation and just say the probability of event y. And we had that as being q multiplied by p plus 1 minus q. And what we want to do is rearrange this to get an expression for p so we can use our sample proportion of respondents who say yes as an estimate of our population proportion who say yes. So what we're going to do is divide through by q, subtract 1, and add on q. And that will give us p is the probability of y divided by q minus 1 plus q. So this is an expression in terms of the true population proportions. And if we want to turn this into an estimate, we then say our estimator of p, so capital P hat, is going to be the sample mean of our yes responses divided by q minus 1 plus q. So just doing a direct substitution in here, where y bar is 1 over n times the sum from I is 1 to n of each of our responses. Okay, and this gives us our method of moments estimator, capital P hat. The next part of the question asks us to explain why q equals 0 or q equals 1 would be unsuitable in this study design. And these have different reasons behind them. If q is equal to 1, then every student is replying honestly to every question. And so we've got no plausible deniability within our data. We've afforded people no privacy. What we effectively done is reduce this to a direct response survey. At the other extreme, if q is equal to 0, then every student replies randomly. What we'll get is the proportion q of students replying yes and 1 minus q saying no. And we've got no information in there about the actual population proportion. So we've gone too far the other way. Our data is just noise. And sort of a smaller additional reason to that, where this would fall apart, is that our method of moments estimate here requires dividing by q. So our estimator isn't even well defined when q is equal to 0, where at least it is defined for q equal to 1. Okay, and then the final part of the question asks us which values of q, so our randomization proportion, will lead to a method of moments estimator, p hat, that gives a valid probability. So just recalling from further up, our method of moments estimator, p hat, is going to be the sample mean divided by q minus 1 plus q. And for this to be a valid probability, what we require is for this to be somewhere in the interval between 0 and 1. Okay, and it's not straightforward to check that this condition is satisfied before running the study and before q is chosen, because we don't know what value q is going to have, so we have to investigate any possible value of q, and we don't know what sample mean we're going to get, because we haven't yet run the study. And this gets additionally tricky because the distribution of this sample mean is going to depend not only on the unknown population proportion p, but also on our randomization probability q. So we have this nice condition, but checking that condition holds is not straightforward. Okay, and finally, we're asked to actually use some real data to come up with a point estimate for this population proportion of study drug users. And what we get is a summary of the data collected. We know that 150 students were asked, the randomization proportion was 0.4, and that we got 99 no's coming out of this as our responses. So in this case, what we have is that y bar, our sample mean, would be 1 minus 99 over 150. So that's just the sample proportion that said yes. That's 51 over 150. And we can use this as our plug-in estimate for the population proportion. So taking this sample proportion, we're going to substitute that in to get our method of moments estimator p hat, which I will scroll back up to remind myself of. It's y bar over q minus 1 plus q. That's y bar over q minus 1 plus q. Yes. Minus 1 plus q. So substituting in our values there, we get this as 51 over 50. That's our y bar, times by 10 over 4, so equivalent to dividing by 4/10. Going to take one off and add on 4/10. And if we work through that algebra, what this works out to be is 15 over 60, or a quarter. About 25% of students we think are taking study drugs within the population based on this sample. Okay, I hope that seeing that work through slowly was helpful for you, and I'll see you in the office hour or in the live session next week. Thank you.